Okay, not sure where the video cut off. The current in a magnetic field experiences a force perpendicular to both. That means both the direction of the current and the direction of the magnetic field. Okay, and we actually wrote that down. This is what the law looks like. It's a cross product of the current and the magnetic field, these being vectors. Current in the direction, magnetic field in some direction. Okay, a current segment, that means in the thing that we did, a short segment of that wire will produce a magnetic field at the position of the compass, okay, that's perpendicular both to the current and the vector from that segment to the compass. Okay? Now, you've got a long wire, so you've got a bunch of segments, so they add up, much like the forces from an electric field from a bunch of different points, right? So it's a simple law. And it's all right, delta I cross R over R squared. Okay? Where R is the vector. And it's got obviously a direction. And if you integrate this or sum it up over all current segments, it gives you the total magnetic field. So you can kind of remember that. But we'll do that in detail with examples in class. Okay? So at least understand that if you've got a segment delta I in that wire and the compass is down here someplace, take the vector from here to here, right? Okay? And I screwed up something here, but I'll fix it. Should be an R cubed. You take that vector and cross it with the current. Current cross this. There's the direction of your magnetic field, and that's why the compass deflected perpendicular to the direction of the wire. Okay, we'll do that in detail. Now, I'll do this. Current times a unit vector in the direction. Okay? And then it's inverse square law. Okay? So the more current, or the, and the delta I is like an I delta S, where delta S is a vector in the direction of the current. Okay? Again, we'll work out the details. That's what it's going to look like. But this you've seen, and I'm going to want you to just play around with for the rest of the lab. Okay? See what you can find. Okay? Then, a changing magnetic flux in a loop, and it's a closed loop. I guess I better put the word closed in there. I'll say potential, it produces a potential difference around the loop. So if that loop happens to be a conductor, you're going to get a current around that loop. Okay? And the law there is very, very simple. I'm going to use kind of a capital E for EMF, electromotive force, but just think potential difference. Okay? It's just the time rate of change of the magnetic flux. So if you can write an equation in terms of time for the magnetic flux, which you could easily for what I just did there, moving the magnet closer and further away, if you make assumptions on the velocity, and understand the magnetic field of the magnet, which is a little more complex, okay? You just take the derivative of that with respect to t, and that tells you how much electrical flux at a given instant, okay? And I'll mention another way to create flux is to take that coil and rotate it in a magnetic field. The thing rotates 180 degrees, and the magnetic field's gone through the loop in the opposite direction, right? If you look inside those generators, you'll see a bunch of gears that make just that happen. And that's how those generators work. They're rotating a coil in a magnetic field. Okay? Okay, let's see, what else do we see?